Okay, so many of you know me from the context of the Prepare project, which I've been an active participant in for many years. But today I'm going to talk to you with a different hat on. So I've also been working on another project called RiftVolc for many years. And this is concerned with volcanoes in the East African Rift Zone. And particularly, we've been working with our partners in Ethiopia. So if we're going to talk about volcanoes in the East African Rift Zone, we have to mention the most widely known example. That's the volcano Nyiragongo in the Democratic Republic of Congo. And this is sort of a perfect storm in terms of hazard, exposure, and vulnerability. So this is the most productive volcano in the East African Rift. There's been 30 major eruptions in the last 100 years alone. In terms of exposure, there is a major city, the city of Goma, with 2 million residents, that's located at the base of the volcano, and that's right where the lava flows from eruptions flow. And in terms of vulnerability, the crisis management here is really complicated by armed conflicts, poverty, malnutrition, and in recent years by COVID-19 as well. So this combination has led to several recent deadly eruptions, most notably in 2002 and 2021. But I'm not going to talk very much more about Nyiragongo. It's very unusual in terms of the East African Rift context, and it's sort of a case in itself. What I want to talk about is the rest of the East African Rift, where actually awareness of volcanic hazards is much, much lower. So there are about 70 volcanoes in the rest of the East African Rift, and 21 of them have erupted historically, by which we mean since about 1800 in this case. The largest of these eruptions was a VEI4 eruption of a volcano called Dubi in 1861. But we know relatively little about them. So a recent 2015 report from the UN, the Global Assessment of Risk, estimated there's about 4 million people living within 10 kilometers of a volcano. And that's the sort of distance that we might expect to be affected by things like pyroclastic flows and mud flows. And 120 million people within 100 kilometers. And that's the sort of distance we might expect people to be affected by things like ash clouds. And the figure you can see on the right-hand side of the screen there, I know the text is too small to read, but there's a list of volcanoes. It's just a snapshot from that global assessment of risk. And what I want you to notice is how large those error bars are. We know so little about these volcanoes, we can't really tell whether they have low hazards or extremely high hazards. And that's basically because we just don't have enough information. And the reason for that is actually there haven't been very many recent eruptions. So what I've plotted here is just the eruptions that have occurred since 1950, since the Second World War, basically, which is what we consider the instrumental era. And actually most of the eruptions have occurred in this Afar depression, which is in the very northern part of Ethiopia and Eritrea. And it's a low-lying desert region, and it's very sparsely populated. So even in this remote region, actually the eruptions have caused significant amounts of damage. So the 2011 eruption of Nabro, which lies right on the border between Ethiopia and Eritrea, destroyed 2 villages. The economic losses were estimated about $3 million. There were at least 7 fatalities, and 12,000 residents were self-evacuated. And that's an incredibly sparsely populated region. But we're also concerned with what's happening at these other volcanoes. So we know they've had historical eruptions, and several of them lie in these densely populated regions of the main Ethiopian Rift and Kenya. And for many years, people have considered that they were simply dormant. That's not the case anymore. Since about 2003, we've been able to use satellite techniques to monitor ground deformation over large areas. So ground deformation is not the same as an eruption, and it's not a hazardous in itself. But it is a sign that there is magma, in terms of volcanoes at least, it's a sign that there is magma moving shallowly underground. And what these satellite surveys have shown us is that there's many of the volcanoes are actually deforming. They've got magma actively moving beneath them. And we've identified 17 deforming volcanoes in the past 20 or so years. And we've seen lots and lots of different magmatic processes. I've just picked one example here. This is Korbeti volcano, and you can see the large town of Hawassa just in the background there. So Korbeti has been uplifting at a rate of 6 centimeters a year since 2009. And if we try and do some back of the envelope volume calculations, that's equivalent to a volume of magma of about 0.2 of a cubic kilometer, which is enough to fill Wembley, a large football stadium such as Wembley, about 200 times. These are very large magma volumes we're talking about here. So these observations were really what motivated projects like RIFVolc and other projects as well, to try and understand more about these volcanoes and what's happening. So one of the things that we've been doing is using various geophysical and geochemical methods to try and image the distribution of fluids within the crust. And of course, we're particularly interested in magma. So what we've seen is that there is high melt fractions, so that means partially molten rock, all throughout the crust beneath these volcanoes. And in the top 5 or 10 kilometers, it's feeding permanent magmatic and hydrothermal systems. So there is definitely magma underneath the surface. We can also look in more detail at the current activity, and one of the tools that's most often used by volcano observatories is seismicity. This is their sort of go-to indication of magma movement. So Ethiopia has a very good national network, real-time national network, but it's really designed at looking at tectonic earthquakes, and it has a detection threshold of magnitude 3.5. Now, most volcanic earthquakes are actually much smaller than that. And what we've been working with Professor Atale Ayeli from Addis Ababa University for many years now to carry out temporary deployments at several of the volcanoes. And they've identified thousands and thousands of small magnitude less than 3 earthquakes beneath the volcanic centers. They've also identified low frequency events and swarms, which are really characteristic of magma movement. So this shows us that the magma is not only there, but it's moving around. But it's really important to note that this is not long-term monitoring. These short-term deployments that's been carried out with international partners, and there is still no long-term funding for this activity. So the other question you might want to ask is how big are these eruptions? What do they look like? How often do they occur? And the way we can get at that is to look at past eruptions that occurred before the historical record using geological tools. And you can carry out very detailed field studies that can map and date ash layers from past eruptions. So it's not possible to do this at all the volcanoes in the East African Rift, but we've done it at a few of them. And one of those is Aluto volcano. And the estimates there are there's between 1 and 3 events, 1 and 3 eruptions per 1,000 years. The typical magnitude of those eruptions is between magnitude VEI 3 and 4. And these events probably occur in clusters. And the last one of those clusters was about 3,500 years ago. So this clustering may actually be one of the reasons why we haven't seen many eruptions in this area recently. But if there are eruptions, they could occur in clusters. So what does this mean in terms of actual hazards? Well, eruption hazards are quite different from seismic hazards. Eruptions typically last several years, and they are inherently multi-hazard. So I'm just going to take you through one type of eruption that we've worked on recently, and that's the formation of pumice cones. And we can look at the geological record and try and interpret what happened to form these pumice cones. So we think the eruptions start with a very violent eruption. So this is a big column of ash going up into the stratosphere. And that's going to cause a pumice fall deposit over a wide area. So that's ash and fragments of rock. And you can see from this assessment here, up to over a meter of ash and rock over a radius of about 50 kilometers from the volcano. So this is going to have a very serious impact on infrastructure in particular, and on human health. As the magnitude of the eruption starts to wane, that eruption column is going to collapse, and it's going to generate pyroclastic flows. And these are the most deadly type of volcanic hazard. They are incredibly hot, they move very quickly, and they will kill anything in their path. So there's no escaping pyroclastic flows. And this, you can see now, is a map of the inundation areas that might be affected by pyroclastic flows if an eruption were to occur. And then finally, as the eruption continues to wane, you are likely to get lava flows. These are much more slow moving. They don't pose much of a hazard to human life, but they are, again, very destructive to infrastructure, particularly things that might be located on the volcano, such as geothermal power stations. And finally, all the ash from this eruption that's lying around is going to be extremely hazardous in the long term, particularly during rainy seasons when the ash can form mud flows known as lahars. So these eruptions are incredibly multi-hazard. And so the way that volcano observatories typically deal with those is using something called an event tree. So this is just a framework to think through all the different scenarios that might follow on and what might occur. And so you can see an example here. This is an example from Aluto, which is the only place that this has, to my knowledge, been attempted so far. So it goes through things like the magnitude of the eruption, the type of hazard, the direction and the location that those flows would go in, and aims to put together probabilities over different recurrence intervals. But the problem with Africa is even at Oluto, which is one of the places that we've studied the most in recent years, the uncertainty is still enormous. So our best estimates for Oluto are in the next 50 years, the probability of a silicic eruption is somewhere between 2 and 35%. That's an order of magnitude range. We don't really know. And the probability of a pyroclastic flow is somewhere between 2 and 23%. Once again, that's a huge range of uncertainty. So I'm going to finish there with some quick conclusions. So in the past decade or so, multidisciplinary studies have unearthed this rich history of volcanic activity and unrest in the densely populated East African rift system. These volcanoes were previously thought to be dormant, and we've actually now shown they're definitely not dormant. And we've been able to understand quite a lot about the characteristics of the volcanic plumbing systems, and we provide the foundation for hazard assessments. That's not the same as performing hazard assessments. So this raised awareness is really driving a shift from crisis response to reducing disaster risk, but actually there's still a huge lack of institutional and human capacity. That means that the baseline data that we have are really sparse, except at a few selected volcanoes where we've been working really intensely, and the uncertainties, even at those volcanoes, are still very high. So mitigating volcanic hazards in this region remains really challenging. If you want to read more about the things I've been talking about today, we recently published an open access review article, and I'll post a link to that in the chat in just a second. So thank you.
Thanks very much, Juliet. Perfect time. And first of all, very interesting presentation. I think we've got a couple of minutes for questions from the audience. So I would like to encourage everyone to type the question in the chat, and I will convey that to the speaker. In the meantime, while waiting, can I just ask, because I was intrigued by your comment that volcanic risk might be high, might be low, but there's no, enough clarity in quantifying it. So in your opinion, what should be the first type of investment, scientific and but even in terms of resources, to be able to reduce the uncertainty with respect to hazard quantification, the volcanic one?
Well, there's two big areas that we always identify. One of them is to establish eruption records. So how often do these volcanoes erupt, and what kind of eruptions are they? And that's really done through geology detailed field studies. And the second priority is monitoring, so we can actually see what's changing at these volcanoes in real time. But neither of those are cheap, and there's a large number of volcanoes to cover. Yeah,
I understand that. This is a really very interesting study. As I don't currently see a question in the chat, unless I'm mistaken, probably we can proceed with the next presentation after thanking Juliet, who will be able, I'm sure, to answer the questions if they arise in the chat. So thanks again, Juliet.